Maybe you've heard that reactions have what's called an activation energy, which is an energy hurdle that the molecules have to get over in order to complete the reaction. But have you ever wondered, how do we know the activation energy? I mean, we're talking about teeny tiny molecules I can't see, exchanging little bits of energy I can't see. So how does anybody actually know what the activation energy is? Well, if you've ever wondered that, you're in the right place. Everybody, welcome to AP Chemistry section 5.6, all about reaction energy profiles and activation energy. In this video, we're going to look at some reaction energy profiles and we're going to learn how to label them properly. Then we're going to take a look at activation energy and how our good friend Svante Arrhenius allows us to calculate the activation energy. So grab your pencils, you're going to need it, and let's get started. First, as we often do, let's take a look at our learning objective, which is to represent the activation energy and overall energy change in an elementary reaction using a reaction energy profile. Elementary reactions typically involve the breaking of some bonds and the formation of new ones. The reaction coordinate is the axis along which the complex set of motions involved in rearranging reactants to form products can be plotted. The energy profile gives the energy along the reaction coordinate, which typically proceeds from reactants through a transition state to the products. The energy difference between the reactants and the transition state is the activation energy for the forward reaction. And finally, the rate of an elementary reaction is temperature dependent because the proportion of particle collisions that are energetic enough to reach the transition state varies with temperature. The Arrhenius equation relates the temperature dependence of the rate of an elementary reaction to the activation energy, there it is, needed by molecular collisions to reach the transition state. Okay, let's dive right into it. We're going to start by looking at a reaction energy profile we've seen before. If you've watched previous videos in this unit, you'll recognize this. Typically we have two reactants. They have to collide in order to react. When they collide, they reach a transition state, which is kind of like a high energy situation. They're not the reactants anymore. They're not the products they're going to be, but they're kind of in transition. And so that usually is represented by a higher energy situation or an energy hurdle that the molecules have to undergo. But again, molecules have to collide, break some bonds, reform new ones, and then we're off to the other side of the hurdle. Okay, this energy difference has been labeled for us. It's plus 132 kilojoules per mole, and that is the activation energy. EA is the symbol we use. The difference between here and getting over that hurdle is the activation energy. Now, you could also say activation energy for the reverse reaction. What if we start over here and want to go back? Well, it might make sense that if we go down a big hill over here, that we're going to have to go up a really big hill on the way back. And the activation energy for the reverse reaction is, again, the start to the top of the hurdle. Keep that in mind. You may be asked questions about that. The difference in start to finish is the energy of reaction, or the delta H. You might label it like that. And in this case, it's negative because we're going downhill overall. One of the guiding questions that has been burning in the back of your mind, I'm sure, because you're very curious and smart, how do we know the activation energy for a reaction? So we're going to get there, but first, a couple of definitions. In case you need these, the activation energy is the amount of energy needed to overcome the energy barrier and move the molecules through the transition state. The transition state is the arrangement of molecules at the point of highest energies. Whatever it happens to be, each reaction is slightly different, unique to its own molecules, and so there's some transition state we got to get through. The reaction energy profile is a graph that represents the relative energies of reactants and products, the transition state, and the activation energy. So again, they come in many forms. This is just one of them that I like to use because it's colorful and informative. But let's look at another specific reaction, just in theory. I don't know if you're aware, but there are two kinds of butene. There is cis-2-butene, in which case the carbons are on the same side of the double bond. And there's trans-2-butene, in which case the end carbons are on the opposite sides of that double bond. And in order for one to become the other, the molecule has to actually change and break its double bond. Remember that a double bond is a sigma bond between the atoms and a pi bond above and below the other two atoms. And it has to break that bond, rotate, and then make the bond again. So Breaking of bonds requires energy going in. Reforming bonds requires energy coming back out. So really, it's about which one is winning. But the transition state is this high energy situation where the bond has broken, but it hasn't formed again. And a reaction energy profile for this reaction actually shows a very minimal change in enthalpy. But in order to break that bond, 262 kilojoules, and this is per mole of molecules, goes into making the activated complex. Once it gets around and reforms, negative 266 comes back out for a difference of -4 on a reaction like. So it looks a little different, but it's got similar information on it. We'll see multi-step reaction profiles in a later episode, but you might see reaction profiles with maybe 2 humps or 3 humps. And in which case, that indicates that this is not an elementary step. This is more of a full process, maybe involving 2 elementary steps. Maybe this one has a big activation energy and we make an intermediate, and then with a minimum amount of energy, we can keep going and get to the products. So we'll see more of the multi-step diagrams in a future episode. Okay, but first, let's take a look at a couple of questions you might be asked. And we're going to do a little pause the video as well. So here's a blank energy profile. The only thing that's on it is the reactants, and they've just given us some level. Notice it's not labeled at this point. So often these are very general, just trying to get a point across, whether it's endothermic or exothermic. If the enthalpy change for this reaction is negative 284, that involves exothermic. Sketch a reasonable reaction energy profile to the right of the line that indicates the start of the reaction. So when you are asked to draw one of these, a couple of things. Make sure your final level is in the appropriate place relative to the initial level. So if it's endothermic, you're going to end up higher up. Exothermic, you're going to end up lower down. And then also make sure you give some kind of transition state energy, activation energy hump to go over. So I'll do this first one. And this is something that I would draw. Now, it's not really told what the activation energy is, but as long as you have a hump there to go over, that's getting the point across. And then we end up 284 lower than we started with because the reaction was exothermic. Okay, your turn. On the generalized reaction energy profile above, sketch a reasonable line or curve that connects the reactants to the products. Take a moment, pause the video, make a quick sketch, and I'll see you back here in a second. All right, and again, these are meant to be fairly general, just getting a visual point across, and so we end up with something that looks like this. Sometimes they are labeled, as you'll see in the questions at the end, with actual numbers that we can use to find the activation energy. But for something like this, very, very general. Apologies in advance if I get a little extra excited about this part, because I'm a nerd and this stuff really gets me going. So we're going back to this question. How do we know that activation energy for a reaction? How do I know that the cis-2-butene changing to a trans needs 262 kilojoules? How do we know that? Well, let's get into it. Recall that there are 4 factors that affect the rate of reaction: the concentration of the reactants, the temperature at which the reaction occurs, the surface area exposed to the reaction. So if it's ground up real fine and lots of surface area, it goes faster, and the presence of a catalyst. All right, so great. What we're talking about today, though, is number 2, the temperature. It's really all about the temperature right now. And so we've seen charts like this before. This is a Maxwell-Boltzmann distribution. Make sure to remember that just so you can drop it in conversation and makes you sound smart. And here we go. Kinetic energy along this axis, the number of molecules on this axis. At a lower temperature, you might have a small fraction of molecules that can pass the activation energy or the minimum kinetic energy required to react. But if you raise the temperature, this whole mountain shifts. The area under the curve stays the same, but a greater fraction are now over past that line. And so the reaction can happen. We have more effective collisions happening, and the reaction generally happens faster. Okay, great. How does that help me to find the activation energy? Because, let's go back. Because I want you to point out that line doesn't really change. For a given reaction, the activation energy is pretty constant. Those molecules have to get over that hump, whether they're going slow or fast. They just have to do it. So that line, keep that in mind. Our good friend Svante Arrhenius, who spent his time traveling around Europe and studying and learning a lot of really cool things, was able to quantify the relationship between the rate constant and the temperature and the activation energy. And so this is what's generally called the Arrhenius equation. And it's one version of the Arrhenius equation, but it's not that useful in this particular form. It goes like this. The rate constant for a reaction is equal to some frequency factor, that's loosely like the percent of effective collisions out of the total there are, times E raised to the negative EA over RT. EA is the activation energy, R is this many kilojoules or joules per mole Kelvin, and temperature is in kelvins. Make a note of that real quick. And that's great and all, but if we don't know the frequency factor, what are we supposed to do? Well, we can rearrange this, and then we get this thing. Basically, we rearrange it by taking the natural log of both sides. So now I get natural log of K equals EA over R, that's negative, times 1 over T plus the ln of A. And if your spidey sense is tingling right now, like, that looks suspiciously like a straight line equation, Mr. Rudolph, you are right. Because that is in the form y equals mx plus b. And we actually have a useful equation out of this. A plot of natural log of K versus 1 over T, y over an x, gives you a straight line with the slope that is the negative of the activation energy over R. So we get plots that look like this. Notice natural log of K, 1 over T. It becomes a straight line. The y-intercept is the natural log of that frequency factor. So if you're wondering, how do we know the frequency factor? Find the y-intercept. It's the natural log of A. And the slope is negative EA over R. So once we get a line, it's pretty easy to find a slope. Lots of times our computers do it for us. And that's just equal to the activation energy over R. So how do we use this? Say I have a reaction. I want to know its activation energy. So here's what we do. We run the reaction at a few different temperatures. Do the same thing, same concentration, same everything, and just raise the temperature or lower the temperature, and we get a range. And what happens is the rate constants change depending on the temperature. So the rate constant is found at each of the temperatures. A plot of K versus T does not give us useful information. Sorry, it's not going to be a straight line. It's going to be curved and not helpful. But we take our data, and those rate constants we got, we take the natural logs of them. Then we take the inverses of the temperatures in Kelvin and we make a plot. And we should get a straight line whose negative slope is equal to negative EA over R. And again, there's R value right there. So the slope tells us the magnitude of the activation energy. And a big slope has a bigger activation energy. A smaller slope has a smaller activation energy. And it's simple and complex and wonderful as that. So thank you, Svante Arrhenius. I just want to note, before we get into the problems at the end of the video here, that there is an exclusion statement. It says calculations involving the Arrhenius equation will not be assessed on the AP exam. It used to be, but now it's not anymore. So you might be thinking, well, great, why do I have to worry about this? Well, the concept is going to be on the exam. The actual calculation using that equation, not on the exam. So just to point that out. All right, let's get into some questions here. First, increasing the temperature of a reaction increases the reaction rate by doing what of those three things? Take a moment and see what you think about the answers to 1, 2, and 3. Okay, yes, it increases the frequency of collisions, and yes, it increases the kinetic energy of collision, but it does not decrease the potential energy of the collision. So we're looking at letter B as our exam. And this next one, I'm going to see if you were paying attention just a few minutes ago. Which graph shows the relationship between activation energy and temperature? Take a moment, think about it. See you back here in a sec. All right, if your spidey sense is tingling that this seems like a trick question, you're right. This question makes you want to think that you have to pick something where one affects the other. But in fact, it doesn't, because remember that line, the number of molecules going over that line does change, but the actual line, the activation energy, doesn't change. So at different temperatures, wow, that's exciting. Nothing's going on there. But that's, they're testing to see how well we know that. All right, consider the following PE diagram for a reversible reaction. Which of the following describes this reaction? So we've got reverse and forward 2 times, 30 and 40 2 times, and then the delta H is plus or minus 10. So let's figure this out. Okay, so we're going forward. In the forward reaction, we end up going down 10. So we're looking for forward minus 10. B has that. Okay. But let's look at the activation energy. From 20 up to 50, that's only an activation energy of 30. So I don't see any combination where the forward is 30 and we get a negative 10 out of it. So lots of information here to sift through. Let's try the reverse reaction. Going from here to here, we have to go up 40, from 10 to 50, and we end up going plus 10. So in the reverse reaction, we're going up 40, and it's plus 10. So D is our answer on that. Okay. 2 more. Consider the following potential energy diagram for a reversible reaction. Here it is again. And we have 20, 10, and 35 as our peak up there. Calculate the activation energy for the forward reaction. All right. To do this, might be a free response question, but you just look and say, all right, we're starting at 20, ending at 35, so the activation energy is 15. And the units should be kilojoules. Calculate delta H for the forward reaction. So this right here, remember, is EA. This here is delta H, the difference from start to finish. And so delta H goes from 20 to 10, and it's going in the negative direction. So delta H is negative 10. And then calculate the activation energy for the reverse reaction, going from here up and over the peak back to the start. Give you a second, pause the video, and I'll see you back here in a second. All right, and if you came up with 25 kilojoules, then congratulations. And you might have noticed that this activation energy for the reverse reaction is actually the sum of the delta H and the activation energy for the forward reaction. We had to go up 15, and then we ended up down 10, so that's a difference of 25 on the scale. So, good job if you saw that. And on the diagram above, sketch a curve that would result when a catalyst is added. So we're going to talk about catalysts a little bit more. And what a catalyst does is it doesn't change the start and finish. This is a little preview. What it does do is it changes the energy requirement. A catalyst often speeds up a reaction because it lowers the activation energy and allows more molecules to get over that hump. So that's a little preview. More detail on that coming up in a later episode. Last 2 questions here, guys. Again, no Arrhenius equation, but here's the question. A student determined the rate constant for reaction at several temperatures. In order to determine the activation energy for the reaction, she made the plot above. What is the appropriate label for the vertical axis of this graph? In order to get the activation energies, what would you label it? Take a moment and think about it. And if you paid attention and said that the natural log of K is what we need over there, then congratulations. And then how would the student find the activation energy using this graph? This graph has a negative slope, which we would set equal to negative EA over R, which is letter C. And that's how you do it. Again, probably not having to calculate it, although you may do a lab to find the activation energy. The concept is what's really important here. So hope you found this helpful. Looking at potential energy diagrams and activation energy. If you have any questions, let me know in the comments. And in the meantime, happy studying and have a great day.